Okay, this is a little different than some of my other videos, but I wanted to provide a quick little like mini lesson on how to approach Gauss's law problems. Just so I guess for your reference to study for the midterm. So from the description of Gauss's law, you hopefully have seen this integral at this point. This E dot dA is equal to Q enclosed over epsilon naught. Now the question that we're going to ask is when do we actually use this and why do we need it? So in general, the way you use Gauss's law is if you see a problem in which you need to solve for the electric field, and the problem you have is highly symmetric, then this is probably where you want to apply this. Gauss's law also goes hand in hand with some conductor problems that I won't be talking about it in this video. So I'll comment really quickly on what I mean by high symmetry problems. So with a lot of these Gauss's law problems, we want to be able to draw a surface or some Gaussian surface around where our charge is coming from. So an example of a good problem would be maybe this problem of like a point charge, and then we want to find the field around the outside. This would be really easy because as we'll see in a little bit, the Gaussian surface you can draw around this is literally just a sphere. Maybe problems where this isn't as good, but you can solve in other means, is something as simple as maybe 2-point charges, somewhere like this. And then maybe it isn't obvious what a great surface would be unless you're solving for maybe right in the middle or something like that. So when you are looking at problems and it's asked you to find the electric field and you have something of like a uniform charge density and it's usually infinite or something that's very symmetric, this is where you would apply Gauss's law. So let's talk about this first. What does E dot dA actually mean? So this is an expression that is going to tell us about the flux. And oftentimes when we solve our Gauss's law problems, we end up in a situation in which, while generally this could be very complicated, in certain scenarios, we can rewrite this as E times A, where A is the area of our Gaussian surface of which the electric field permeates through, and E is the electric field. This, you might remember, is very related to flux. So how should we think about this? I have a 2D drawing here of an infinite wire. Imagine that it's like infinitely going into the plane, and it has maybe some charge like Q or something. Then this should be a complete sphere, sort of truncated in my drawing. How is the electric field going to interact with this surface that I've drawn? Well, we know that it should radiate out sort of symmetrically. So maybe we'll have a field line that goes like this, and it goes like this in every direction. So these are our electric field vectors. We should be getting some like E being a function of R. And it's going to point radially outward. So I'm going to write this as ER hat. Maybe just to be extremely correct, I'll make this a function because it should depend on the distance. And then what does dA mean? So formally what dA is if we take an infinitesimal surface, then dA will characterize the surface by being a vector that is normal to the surface. So dA points in the direction of a normal vector to the surface. So I'm going to draw the normal vector in purple. So on the sphere, the normal vectors on like low infinitesimal part would point like straight up like this in the r hat direction. So then you'll notice, because dA points in the r hat direction, and E points in the r hat direction, the integral of E, or the dot product actually, of E dot dA, charge really quick. This dot product of E dot dA is really easy to calculate. And this is sort of the trick that we need in all of our Gauss's law problems. And in this scenario, then we often are able to extract this very nice quantity, just E times whatever the area of our Gaussian surface is. So there's very few problems that we have done that will sort of allow for this. Let's just go over them very quickly. So there's 3 symmetries you should be aware of: spherical, planar, and cylindrical. So let's consider this like spherical problem. So you might imagine just as we drew above, but now not a long wire, but like a big sphere. We should have these electric field lines sort of radiate out of the sphere. These are sort of very poorly drawn. We can imagine them coming out of the sphere. In this case, our Gaussian surface. So Gaussian surface is a sphere. The surface area of the sphere is 4 pi r squared. So therefore, in spherical symmetric cases, E dot dA will give us E times 4 pi r squared. So now let's go to the case of an infinite plane. So let's say like this could be like a sheet of charge. The Gaussian surface you would draw is maybe a pillbox. So here I've drawn like this little cylinder, that surface area. You could also just like, I guess, draw a box as well that cuts through the surface. Well, what matters is that it has some sort of like, in this case of the pillbox, the surface area of the circular part is A. So our Gaussian surface is a box or a pillbox. And the surface area, I'm just going to say is A. Maybe I'll draw the electric field lines here so it's sort of clear what's happening. So it's sort of permeating through the surface. And there's also going to be some amount going down to the bottom as well. So we have to enclose the whole space. So in this case, the integral of E dot dA is going to be E times 2A. We have a contribution of 2 here because if we look at this sheet, there's electric field going through the top and electric field going through the bottom. And since this pillbox encloses that space to enclose some charge, we have to account for both of that. So finally, let's go to the some cylindrical symmetry. So this is like the infinite wire. I've drawn it not like on the face side cut, but now a little more 3D, where the electric field just sort of be permeating through the sides like this, and I guess also through that. So the Gaussian surface is a cylinder, and the surface area is 2 pi r L, where L is like just the length of the cylinder we're dealing with. So therefore, the integral of E dot dA should be E times 2 pi r L. So now that we've done this, we can look at some example problems to see how this might come into play. So let's do spherical symmetry first. Let's imagine we have a uniformly charged sphere of a charge density rho and radius r. And I'm asking what is the electric field at some smaller r relative to big R. So I'm going to first draw our surface, albeit somewhat poorly. So we have this inner thing of radius r, and it's going to be a sphere. So if this is a uniformly charged sphere, I'm going to argue here that the electric field along the surface of the sphere should be the same everywhere in terms of magnitude. So with that argument, we have the integral of E dot dA, and by Gauss's law, this should be equal to Q enclosed over epsilon naught. So let's solve for Q enclosed first. So this should be rho times whatever like the volume that we enclose is, right? Because rho is a charge density. Rho is going to be in units of charge over volume. So we need to only find the volume of the sphere that we have. So in this case, that should be 4/3 pi r cubed. And we're using small r here because we only care about the sphere. So using our symmetry argument, the left-hand side should become E times the surface area, which is 4 pi r squared. Now we can apply some cancellations. And we get that the magnitude of the electric field is equal to rho r over 3 epsilon naught. So what direction does this field go in? It should be in the r hat direction, right? Because if we look back at our drawing, we have this uniform magnitude electric field that goes out radially from the center. I'll point out really quickly, maybe this answer is something that you're used to looking at. So let's imagine if the sphere has a charge Q, then rho, being the charge density, should be Q over the full volume, which I'm going to write as 4/3 pi big R cubed. And then you'll notice if I plug this in, for I'll just do the magnitude to keep things simple. This should give me following. So now I could cancel, do a few cancellations. These three will cancel out. And I get Q R over R over 4 pi epsilon naught. So that's basically the constant K R squared. Or maybe more compactly written in other places like this. And you might notice that, I guess in this first form that I wrote it over here, this is basically like a ratio that tells me a little bit something about the charges as well as some R squared dependence. Great, now let's move on to a sheet of charge. So now we have a infinite sheet of charge. It's drawn finite, but imagine it's infinite. The charge density is going to be sigma. This is going to tell me the charge over the area. So how do I solve this? The first thing I'm going to do is draw my pillbox. And I'm going to say it has an area A through this top surface. I set up my same Gauss law setup. The Q enclosed should be this area here. I'm going to shade it in. This area here, A, times sigma. Because since sigma is a surface charge density, and since we're enclosing an area of A, this will tell me the total charge that I've enclosed. Now I perform this integral. If you remember from what we did above, this gives me 2 times A because the pillbox has an area on top and an area on the bottom. And then the resulting electric field magnitude is just sigma over 2 epsilon naught. And if I call this direction z hat, this should be my final electric field. Finally, we can do the wire. So let's imagine I have an infinite wire. I'll draw it like this, the 3D drawing again. I'm going to construct my Gaussian surface to be the cylinder around it. This is going to have some length L and some radius here. I'm going to call it R. And remember that lambda, the linear charge density, is going to be charge over length. So again, we have this integral of E dot dA. This is going to be equal to Q enclosed over epsilon naught. The enclosed charge is going to be the length of the wire we've enclosed, L, times lambda. And now we can perform the integral on the left-hand side. So as I mentioned before, it's going to be E times the surface area that it goes through, which is 2 pi RL. We have a few cancellations. just of the L. So we get that E is equal to lambda over 2 pi epsilon naught r. And if you remember that this should be the radial direction outward, the vector answer would go as so. You'll notice that in this example and also the example above, the Gaussian surface dimensions, like the L, the length of the cylinder, and A, the area of the pillbox, didn't actually matter. They canceled out. So just remember that when you do a lot of these problems, whatever surface you end up drawing, if you have to define a new physical quantity, it should cancel. So just as a recap, with Gauss's law problems, you're trying to solve the electric field for a very symmetric system. There's three cases that we remember, so I'll scroll back up to that. A spherical symmetry, a planar symmetry, and a cylindrical symmetry. We're going to draw a Gaussian surface in a way where the electric field is uniform in magnitude. And then the integral simplifies, it's just E times whatever area we're dealing with. Then we just figure out what the enclosed charge is, and we can isolate E.